Morning Warriors, this is Mr. Davis here, and we're going to move right into week 8. So, I'm going to give you a little presentation about gravity and motion. So, I want us all to understand in a little bit more detail what we started to understand last week. So, last week we talked about Earth's location in space, and we determined that its gravity. Gravity is the force that's keeping the Earth, Sun, and Moon system doing what it's doing. We talked about how the seasons are generated based on this relationship or the spatial relationship between these three objects. Hopefully, all that made sense to you. If you're stuck on any of that, make sure to send me an email or send me a message on Remind, and we can clarify some of those things. But I'm going to assume that everyone's moving along together with this, and we're going to talk about gravity and motion. So we'll answer a couple of key questions. We're going to figure out what determines the strength of gravity between two objects. So what determines how strong the amount of gravity between two objects is going to be? And what two factors combine to keep the Earth and Moon in orbit? So we'll look at some graphs, and they'll kind of show us what force of gravity is being felt on different objects at different times. So let me move ahead to some of those graphs, and we can start to learn about these two key things right here. So these are the two key things that I just brought up. Also, I would like for you to follow along in your textbook if you want. It'll probably make it easier for you. Go ahead and open your textbook to page 474 and 475. And you'll see those key terms on the top left. And you'll see the figure that we're going to look at on page 475 on the top right. So here's figure 7. And it says gravity, mass, and distance. The strength of the force of gravity between two objects depends on two factors. Those two factors are the masses of the objects and the distance between them. Gravity attracts all objects toward one another. So remember, we learned earlier that a force, which gravity is definitely a force is a push or pull. But gravity is not a push. Gravity is a pulling force, right? So gravity attracts or pulls all objects toward one another. And remember, the electromagnetism, that could be a push or pull. When the magnets are attracting, then they're both pulling towards each other. But remember, when magnets are repelling, then they're pushing each other apart. So keep that in mind. Gravity is a force, but it's only a pull force, not a push force. Excuse me. And if mass increases, force also increases. So the two things that cause the force of gravity are going to be the masses of the two objects and the distance between them. And you can see on the bottom of this, it says if distance increases, force decreases. So if you pull some things apart, the force between them decreases. Now we're going to look at our first chart, and we're going to try to take like kind of a deep dive into this. So you're going to have to pay close attention if this chart doesn't just pop out at you automatically. I'll walk you straight through it, but there's a couple of terms that we have to define here, and I'm going to give you a second to kind of process everything. So I'll read the scenario. The scenario is right here on the right. I'll read this, and I want you to take a look at the graph as I read this scenario, and I'll point out a few things about the graph as we go. As a rocket leaves a planet's surface, the force of gravity between the rocket and the planet changes. Use the graph to answer the following questions. So we haven't gotten to the questions yet. I'll show you those in a second. But let's make sure we understand this graph before we even look at the questions. So I'm going to give you a second to take a look at the x-axis. what does this mean? And the y-axis, what does that mean? So every graph is going to have two axes. So the x-axis right here along the bottom starts from 0 and 1, 2, 3, and 4. But what do those numbers mean? Well, they mean the distance from planet's center. Planet's radius equals 1. So the force of gravity is measured or that distance that we talked about that's related to the force of gravity is measured from the center of the thing that's pulling to the center of the other object that's also pulling. So if you want to visualize that, think of a planet. Planet is a huge object and it has a center. So you can think about Earth. Just imagine Earth with nothing on it if it would just happen to be a smooth sphere, right? And it has a center. The length from the center of the planet to any part of the surface of the planet is going to be 1 radius. So you can think about math class. Remember what radius is. It's the distance from the middle of the circle to the edge of the circle, and in fact any edge of the circle. So you can take that math concept and we're going to start applying that to real life. So the distance from the planet's center, planet's radius equals 1. What does that mean? The distance from the center of the planet to any part of the surface is going to be 1. If you were actually in the center of the planet, somehow you dug a hole through all the way to the center of the planet, then you would be at 0. But we're going to make an assumption for our project, for our scenario here, that the rocket is going to begin on the surface of the planet and not at the center of the planet. That's why we're going to start from a distance of 1. And the length of 1 is the radius of that planet. So you can imagine planet Earth with nothing on it. Just say it's just the smooth sphere and our rocket is just resting right on top of it. And it's being pulled towards the center, but it's sitting on the surface. So it's not moving. It's not in motion. It's just sitting with respect to the planet. It's just sitting on top of the surface of the planet. And it's right here on our graph. So if something is just sitting, if our rocket is just sitting on the surface of the planet, then it's at a distance 1 radius from the center, and it's experiencing, so remember we have to look at the y-axis too, it's experiencing a force of gravity on the rocket in millions of newtons. So what's the force of gravity? What's the measurement? Remember, well, let's keep moving. It's sitting there on the surface of the planet, and it's experiencing 4 million newtons just by sitting there. 4 million newtons is the way we express the force of gravity that it's feeling. Now, when that rocket takes off, it's going to go away from the center of the planet. So it doesn't matter which direction up is on that planet. So imagine your planet with a rocket on it. If that rocket takes off in a upward trajectory, meaning away from the center of the planet, it doesn't matter which side of the planet it's on. If it goes straight away from the center of the planet, then it can reach a point that's twice as far from the center of the planet as the surface is. So imagine that a planet like the Earth with a rocket on it, you measure the distance from the center of the planet to the surface where the rocket is sitting, then take that exact same distance and go that far above the planet. So take that distance from the center of the planet to the surface. Now take that same distance and go from the surface of the planet up. That would be 2 radiuses, or 2 radii away from the center of the planet. So when that rocket takes off, it's gonna go from the surface to 2 radii away from the center of the planet. As it makes that trip from the surface to some kind of a height that's equal to the distance from the center of the planet to the surface, from the surface of the planet up, then it will be experiencing a lot less force of gravity. So remember, our y-axis is showing us the force of gravity from that planet. So as that rocket takes off and it gets twice as far from the center as it was when it was resting on the surface, it's now experiencing, it started off with 4 million, then 3 million, then 2 million. Now it's at 1 million newtons. So when we doubled our distance from the center of gravity, we reduced the force of gravity by, we'll just say we divided our force of gravity by 4. So we doubled our distance, but our gravity decreased 4 times. So that should tell you something about distance and gravity. Namely, that doubling the distance reduces the force of gravity by 4 times. So let's take a look at a question. Hopefully everybody kind of gets that. I won't do that with every graph, but I want to make sure that we know what these graphs really mean. So what is the force of gravity on the rocket at the planet's surface? I'll give you a second to answer that. What is the force of gravity on the rocket at the planet's surface? Good. What is the force of gravity on the rocket at a distance of 2 units? Twice the planet's radius from its center. Yeah, 1 million newtons, right there, what we just said. According to the graph, is the relationship between gravity and distance linear or non-linear? Explain. So for this one, you might have to use the textbook because it's asking you something very specific. And you can look at page 476 for this one. But I'll go ahead and just say it. A linear relationship is going to be represented by a straight line, right? A linear relationship would be expressed by a straight line, right? We have a curved line, so we know that this relationship is going to be non-linear. But what does that mean in real life? Well, a linear relationship in real life is something more like, hang on, just give me 1 second. All right, guys. So a linear relationship in real life would be something like if the rocket is 1 radius away, when it doubled its distance, when it increases distance by 1, like say it went 1 additional radius away from the center of the planet, and then its force of gravity dropped by 1 unit, right? And then it went another radius away from the center of the planet, so its distance increased by 1 more radius, then its force of gravity decreased by 1 million newtons. And then it went up by 1 and so forth. So if you had a kind of a line that looked like someone set a ruler down and went diagonally across here, that would be a linear relationship. So it's non-linear. The graph is a curve. In general, how does the force of gravity pulling on the rocket change as the distance between it and the planet increases? So I want you to really take a second and think about this question. Super important to build this connection in your mind about how graphs work. That way, when you get to high school, when you get to college, when you see a graph and you take a look at it, you glance at it, you know what this graph means. So you're not going to be out here, trying to shoot a look to somebody else and see what they think it means. You'll know exactly what that graph that you encounter means. So I'm going to give you a second to really think about this in general. So it's a generalization. How does the force of gravity pulling on the rocket change as the distance between it, the rocket, and the planet increases? So you think about that for a second. did you say something like this? It decreases, right? So that's in general. It decreases. Good. What would the force of gravity on the rocket be at a distance of 5 units? So we're at 1, 2, 3, 4. What if we went off the graph to about here? Where would that line be? So this is 1 million. This is about 500,000, or maybe a little less than 500,000. This is about 1/3 of a million. Where would it be around 5? About 160,000 newtons, or 0.16 million newtons. So hopefully you see that trend. As this thing starts to flatten, right? It doesn't drop all the way out to the bottom. It flattens more slowly as it continues outward, right? So you had a lot of drop in this line as you gain some distance. So between 1 and 2, you can say you divided that number by 4. Between 2 and 3, you can see something going on. But let's see. In general, how does the force of gravity pulling on the rocket change as the distance between it, the rocket, and the planet increases? So how does the force of gravity pulling on the rocket change as the distance between the rocket and the planet increases? How does the force change? Good, it decreases, right? The force decreases as you get further away. And you can see that expressed by this data. What would the force of gravity on the rocket be at a distance of 5 units? We already did that one. Good. So gravity and inertia. Remember, inertia is Newton's first law. So Newton concluded that 2 factors, inertia and gravity, combine to keep Earth in orbit around the sun and the moon in orbit around the Earth. So let's just take a look at the Earth and the moon system. And we're on page 477 now. You can find this diagram. The force of gravity between the Earth and the moon. What is that like? So the moon is traveling in... Oh wait, let's go back. Let's figure out what inertia is. So remember, Newton's first law is inertia, and that law states that objects in motion will stay in motion until acted upon by some outside force. Right? So here's the moon right here in our diagram, and it's moving. It's moving this way. So if the Earth were to disappear, it goes away. Which way would the moon go? This way. It would just keep following this path right here. See that dotted line? That orange dotted line? Boom, it would just follow that path right there. However, the Earth is there. So the moon feels some pull, or the moon is being pulled by the Earth. So instead of going this way, it goes this way. It splits the difference, right? The Earth's inertia, or the motion that it would take if the Earth were gone, is not the actual orbit. It's where it would go if the Earth were gone. And you can see that this thing would just keep circling over and over and over, which it does in real life, because it's, if the Earth weren't there, I want to avoid saying it wants to. But I think maybe it's easy for you to visualize if I say the moon wants to just go this way, but the Earth keeps pulling it. But don't think about it as want. The moon is going in this way if the Earth isn't there. It would go that way, but since the Earth is there, it's getting a pull this way, and its inertia is making it have a trajectory along this path. But it ends up being bent and becomes an orbit because there's a force of gravity being exerted between the Earth and the moon. So that's about it.